In the previous lesson, you have learned that field lines are visual representations of the electric field and that the summation of their numbers is equal to the strength of that particular electric field. When passing through a given region or surface, the number of these field lines depends on three factors. These are the magnitude of the electric field, the surface area, and the angle of orientation of that surface. The relationship among these three is what we call the Gauss's law. In this lesson, we will be talking more about this law and its applications in the field of physics. Published in 1867 by Carl Friedrich Gauss, a German mathematician, Gauss's law contains similarities with Coulomb's law and may be used to derive it. It also forms one of the foundations of Maxwell's equation for classical electrodynamics, which we hope we can still cover in the future. Gauss's law states that in any closed surface, the electric flux is equivalent to the net charge inside the closed surface divided by the inelectric permittivity of free space, which is a constant value. This electric constant establishes the direct proportionality between field intensity and electric displacement in a given region. Let us have a quick recall of the formula of electric flux. Which among these is the formula we need? That is right. Phi sub E is equal to E times A. Gauss's law postulates that the total electric flux passing through a closed surface is considered zero unless the volume enclosed by this surface contains a net charge. We know that the number of field lines entering the surface is equivalent to the number of field lines leaving it, right? Thus, this law establishes the basic relationship between the flux of electric field lines to the charges contained inside a closed surface. But remember, class, an enclosed surface pertained in this law is usually imaginary, hypothetical, or arbitrary. Commonly, this can be called as Gaussian surface. Before we go any further, we understand that we have quite a lot of quantities, symbols, and units discussed already. I have here a table of these quantities that you will encounter in this lesson, and you may take a screenshot of these as your reference. We can apply Gauss's law in identifying electric field of a certain region where there is a symmetrical charge distribution. The direction of the electric field may be identified through these symmetries, which may be in the form of a sphere, a cylinder, or a plane. As such, the most important factor we need to consider when we are using this law is the identification of the symmetry present in a given region. For a spherical Gaussian surface, for example, any given point charge or any spherical charge distribution is distributed in a uniform manner on the surface. We know that in a sphere, the radius r is centered on the region. Again, we mentioned that the symmetry is very important in considering Gaussian surface. What do you think this implies with the direction and magnitude of its electric field? You are right. Throughout the points in our Gaussian surface, the electric field direction is radial, and the magnitude of the electric field is equal. Since the area of the sphere can be computed using 4 pi r squared, we can substitute these in our previous equations as follows. Then, we can calculate the electric field in a sphere using this formula. Let us take a look on another type of enclosed surface, which is a cylindrical Gaussian surface. If in a spherical surface, charges are uniformly distributed, for cylindrical charge density, which we represent as lambda, is uniformly distributed along a long line, such as wire. The whole charge present on the line distributes to the field at any point, thus forming a cylindrical symmetry. What does it say then about the electric field's direction and magnitude? That is right. Since it is still symmetrical, electric field is equal, but the direction becomes coaxial. We can use this equation in calculating the electric field of cylindrical Gaussian surface, where E is the electric field vector, epsilon sub 0 is the electric permittivity of free space, Greek lambda is the linear charge density, and R is the radius. On the other hand, we can use the following equation in solving for its electric flux, where phi sub E is the electric flux, L is the arbitrary length, Greek lambda is the linear charge density, and Greek epsilon is the electric permittivity of free space. In the next video, we will have some practice to work on using the concepts and formula we learned about Gauss's law. But that will be all for this lecture. I am Gilmar De Castro, and see you in the next video.